Hey everyone, welcome back to Checkmate Scholars. In today's video, we're going to be going over the 8th grade 2025 Science STAAR test. Make sure to check the links in the description if you'd like to access your 1 hour of free tutoring, as well as the link to the TEA website where you can access a lot of these practice tests that we go over on this page. All right, let's get started. Before we go over the practice questions, I think it's a bit essential that we go over the primary topics you need to know before you head into the exam. All right, here we're going to be looking at the difference between an atom, a molecule, an element, and a compound. All right, here we have the atom, which is the simplest particle of matter. In other words, if you break down any object as many times as you can, the smallest portion or the smallest component of anything you break down is an atom. Here we have the parts of an atom. So in the center you have the nucleus, which is composed of your protons and your neutrons. Your protons are the positively charged portions, while the neutrons are the neutral portions. On the outside you have your electrons, which are negatively charged. Now a molecule is where you have two or more atoms chemically joined together. Okay, so imagine this atom and another atom joined together. That is a molecule. Okay, that is a molecule. Two or more atoms chemically joined together. Now let's look at an element. An element is a substance made up of only one kind of atom. It cannot be broken down into any other simpler substance. So if you can imagine a pure bar of gold sitting right in front of you, if you were to break it down and look at it under a microscope, you're going to see millions of atoms, but it's going to be millions of the same type of atom, which is gold. So you're going to see millions of small, tiny gold atoms, right, that make up that big block of gold. So that is an element. In that case, the element is gold. Your elements are also going to be present on your periodic table. Lastly, we're going to look at a compound. A compound is a substance made up of two or more different elements chemically joined together. So here, it kind of resembles the compound of water, where you have two hydrogen atoms. That would be the white atoms right here, and the big red one would be your oxygen. So in this case, what two elements did we use? Hydrogen and oxygen. All right. Now we're going to be looking at physical versus chemical changes. A chemical change is not easily reversed. It produces new products and it uses up the reactants. So in this case, we have fire being produced from the burning of wood. When you burn wood, it turns into ash. You cannot reverse ash back into wood. The same way we burn the wood, right? We get a new product, which is ash. In this case, the reactants, the wood, for instance, is used up. So we can't bring back our reactants. Now, oftentimes with chemical changes, you're going to produce heat, light, sound, or fizzing. So an example of heat and light is this wood burning, right? It produces heat and light. Now, what about sound? Whenever you maybe set off a firecracker, for instance, it shoots up into the sky and it creates a loud bang. That bang is formed from the explosion, which is from the chemical elements mixing up with the little spark that you put on the tail of the firecracker. Lastly, we're going to look at fizzing. Fizzing occurs whenever a gas forms. So typically you can see this when you mix some powdery substance with a liquid substance and it forms that fizzing sound. So a good example of this would be whenever, let's say you have water in a cup and you have these vitamin C packets. Whenever you add the vitamin C to the water, it typically fizzes, and that is a chemical reaction taking place. What about electricity? That's also a possible outcome of a chemical change, although it's not as popular as these four up here. But you can think of of electricity being produced as the chemical change present in batteries. So a battery is a bunch of different types of chemicals basically reacting with each other, producing the electricity which powers your phone, your computer, maybe a TV remote or RC car. So different things like that. What about a precipitate? A precipitate is a new substance that is formed when you mix a solvent with a solute. So again, the vitamin C packet and the water, if they are both mixed, and let's say there's too much vitamin C, you can get a precipitate. All right, so a precipitate is just a new substance forming typically around the edge of the cup, maybe when you're mixing a dry substance with a liquid substance. Now let's look at physical changes. Physical changes are easily reversible. You don't produce any new product, and it's often just a change in state. So a good example would be that of water. When you melt ice, right, you get water. But when you freeze the water, you get the ice back. So nothing new has been created. The water is simply just changing state. Here are some other examples of chemical changes versus physical changes. Here we have the melting of an ice cream, right? When you melt the ice cream, yeah, it's liquidy, it's all gluey, but if you put it back in the freezer, it becomes ice cream again. Shredding paper. Shredding paper is not as easy to reverse, although if you have the time, you can super glue all these edges together and get your sheet of paper back. But nothing new has been created. The paper here at the top is still the same paper here. It's just cut into small shreds. A tomato, a slice of tomato is still a tomato, right? So it's still the same tomato that was cut, right? It's just thinner. The boiling of water, as we previously discussed, is just a change of state. Now let's look at combustion, rotting, rusting, and digestion. If we start with rust, right? Whenever you maybe leave something of metal outside exposed to the elements like rain and air, it starts to rust. That rust is a new substance being produced, and typically when you scrape it off, it's gone, but it's rust, right? It's a new substance being produced. What about digestion? Let's say you eat a cookie and it travels to your stomach and it's broken down. That cookie is no longer the same. How do we know that? Well, if you throw it back up, right? Let's say you get a tummy ache and you throw it up, that cookie is no longer the same. It's all gushy and slimy and all sorts of stuff, right? So that cookie is no longer the same. It's different. A new substance has been produced. What about rotting? The rotting of an apple. Well, this is pretty self-explanatory, right? If an apple or a fruit or a vegetable is to rot, then guess what? It's gone. You don't typically save a rotting apple thinking you can reverse the rotting. No, the rotting is a permanent change that cannot be reversed. All right, now let's take a look at your metals, nonmetals, and metalloids. Here, and actually before we do that, remember we spoke about elements? These are your elements. These are all of your elements. Here is gold right here, AU. And so anything that has gold is going to have this element in it. All right. So let's take a look at metals, nonmetals, and metalloids. Your metals are going to be all right here. Okay. All in this pinkish color. These are all of your metals. Your nonmetals are going to be mainly on this side, right? But we're also going to have hydrogen. And then your metalloids are going to be in the middle. Now, what's the difference? Your metals are lustrous. They shine, right? They're pretty shiny. They're good conductors of heat and electricity. They are very dense, more heavier than your nonmetals and metalloids. They have high melting points. So these things, you typically have to heat them up really, really hot before they melt and turn liquid. They are malleable. This is a good property of metals. You can bend them, you can twist them, okay? They are ductile, they can be drawn into wires. They are usually solid at room temperature. And as a thin sheet, they're pretty opaque, they're sonorous. Now let's take a look at your nonmetals. One thing you need to remember is that they are poor conductors, okay? They're non-ductile, which means that it's hard to shape them into wires, and that's because they're brittle. If you try to bend it, guess what? They break. They're also pretty dull, so they don't shine like your metals, okay? They can be solid, liquid, or even gas at room temperature. All right, let's look at your metalloids. Your metalloids look like metal, but they behave like nonmetals. All right, so they're pretty solid at room temperature, and they look like metals, but guess what? They behave like nonmetals. So what does that mean? When you try and bend them, guess what? They're brittle. They break. Okay, they break. They're kind of strong, but not really. They're an okay conductor of electricity and heat. So they look like metals, but they act more like nonmetals. That's why you can see here that they're kind of in the middle between your metals and your nonmetals. All right, let's take a look at particle motion. Now, you have different states of matter. You have your solid, your liquid, and your gas. Okay, now a solid is composed of small particles, right? These are your atoms, okay? Now, a solid is not actually as still as you think. There's a little bit of motion, okay? That's illustrated by these lines right here. There's a little bit of motion, but not a lot. A very, very, very tiny amount of motion, okay? That's why most of the solids that you see, they are pretty stable. They don't move, okay? Now, if you add a little bit of heat, then your solids turn into liquids. So a good example of this would be ice turning into water. Now here you can see that your particles, your atoms, or some may say your molecules are moving around, okay? They are moving around. So that's why if you get a cup of water and you move it around, guess what? It swishes around. Why? Because the particles are more motile. They're no longer just vibrating right next to each other. Now they're moving all over the place. But if you take heat away, if you cool it down, they return back to that solitary place. They calm down. Okay? Now what about gas? This is where your particles lose absolute control. Okay? They're moving all over the place. So if you're to heat up, let's say, some water into vapor, guess what? That vapor is moving all over the place, right? So if you boil some water in a pot and you open the lid, guess what? All that gas is going to escape through the room, right? And it's going to go all over the place. So that's what happens when you add heat. It increases the motion of the particles. But if you take away heat or you cool your gas down, guess what? Your gas turns into a liquid and your liquid turns into a solid. Let's keep moving. Here we have kinetic versus potential energy. One thing to know is that kinetic energy is the energy of motion. That's when you're moving. Potential energy is not moving. This is pretty stationary, but it has as the word implies, the potential to turn into motion. Okay, so potential energy is energy that is stored up. Okay, so if we take a look at this guy riding his bike, as he's going up the hill, he's using kinetic energy, he's moving. But once he's at the top, there's a lot of potential energy. If you've ever ridden your bike to the top of a hill, you'll notice that once you start to come down, you don't even have to pedal. You just move automatically. And that's because there's potential energy here. Okay? There's stored up energy at the top. So once you come down, guess what? All that potential energy is translated to kinetic energy. Same concept here with this ball. At the top of this structure, this ball has a lot of potential energy. There's energy stored up so that once it's released, it moves by itself. This potential energy is turned into kinetic energy as the ball falls. Let's look at Newton's laws of motion. The first law is that a body in motion remains in motion, or a body at rest remains at rest unless acted upon by a force. What does this mean? If you are to, for instance, look at your phone. Let's say your phone is on the table. Your phone is going to remain on that table forever if no one touches it or if nothing happens to the table, right? But the moment you move your phone, The moment you use your hand and you grab your phone with your hand, guess what? Now that phone moves. And it's going to keep moving until you stop moving your hand. All right? So anything in motion is going to continue to stay in motion, while anything at rest is going to continue to stay at rest. Okay? Let's look at the second law. Force equals mass times acceleration. This is a formula you must know. Force equals mass times acceleration. What does this mean? This means that the bigger the mass or the bigger the acceleration, the larger the force. So let's say I have a mass, or what's a good example? Let's use bowling balls, for instance. If you've ever gone bowling, right, you know that heavier bowling balls can knock over more pins, right? They travel with a lot of force, right? So if I have a bowling ball that weighs 10 pounds, and I am able to accelerate that bowling ball by waving it back and driving it forward down the bowling lane at, let's say, 10 miles per hour, that creates a force of 100, okay? But let's say I pick up a heavier bowling ball, a bowling ball that, let's say, weighs 20 pounds. 20 times 10 is what? 200. So we can see that force increases as the mass increases. But what if the mass of the bowling ball stays the same? Let's say I still carry the 10-pound bowling ball, but every time I accelerate it faster. So I throw that bowling ball down the bowling lane, at first at 10 miles per hour, then at 20 miles per hour, then at 100 miles per hour. What's going to happen to the force? It's going to increase, okay? So force equals mass times acceleration. And if you increase the mass or the acceleration, the force is going to increase, okay? So let's say I increase the mass and keep the acceleration the same, the force is going to increase. Let's say I increase the acceleration and keep the mass the same, the force is going to increase. Let's say I increase both the mass and the acceleration, the force is going to increase, right? Lastly, the third law. For every action, there is an equal and opposite reaction. What does this mean? This means that for everything you do, there is an opposite force applied. So if we look at these two ladies with the roller skates, if this lady in tan pushes the lady in red, guess what? This lady in red is going to move backwards, and so is this lady in tan. Why? Because yes, she pushed this lady in red, but at the same time, this lady in red also pushes her back. It's the same concept with jumping. If you jump from the floor into the air, guess what? As your body pushes with force against the ground, right? The ground also pushes you with force, okay? So that's the concept of equal and opposite reactions. All right, now we're going to be looking at motion. You have speed, velocity, and acceleration. Speed is a measure of how quickly distance changes with time, right? So for instance, if you've ever heard of miles per hour, that's just telling you that you've been able to cover an amount of miles in 1 hour. So 60 miles per hour means that in 1 hour you can cover 60 miles, right? That's speed. But velocity is a bit different. Velocity is when you combine your speed with direction. So if you've ever heard of a police chase, you'll hear that the police is saying the suspect is moving 60 miles per hour east, or the suspect is moving 60 miles per hour north. That is velocity. That's telling you the speed and the direction. Now, acceleration is a change in either direction or speed or both, okay? So we oftentimes think of acceleration as speeding up. Let's say a car speeding from 0 to 60 miles per hour. We think that's acceleration, and it is. It's a change in speed, going from 0 miles per hour to 60 miles per hour. But what if we stayed at 60 miles per hour and we turned right? Guess what? That's still acceleration. What if we increased our speed, and turned left. That is still acceleration. Acceleration is a change in speed, direction, or both. Okay? All right, now we're going to look at the parts of the Earth. All right, the layers of the Earth. On the outer portion, we have the crust. This is where we are. Okay, so I think this is Texas right here. So if we were to zoom in, we are standing or sitting on the crust. Underneath the crust is the mantle. This is a very thick layer of solid that flows very slowly. So it's not liquid, it's solid that just flows very slowly. This is what all the crust sits on. Beneath the mantle, you have the outer core, and then you have your inner core. Hey everyone, if you're interested in a free 1-hour tutoring session with Checkmate Scholars, make sure to click the link in the description. That link will send you to a Google document where you can sign up for your student. Alright, let's get back to the video. Alright, let's take a look at the different types of tectonic plate boundaries we have. So here we have the transform boundary. This is where two tectonic plates rub or slide past each other. This is going to cause earthquakes. Then we have the popular boundaries, which are the convergent boundaries. This is where we get the formation of mountains, right? And this also causes the formation of trenches. So if we look here, we see that when one boundary gets pushed underneath the other one, so both of them are coming together, but one gets pushed under the other, this is going to form a trench, okay? It's going to form this deep area of crust underneath the water. All right, let's take a look at divergent boundaries. This is when two tectonic plates separate. This is when they move away from each other. This is going to form a couple of things. You're going to get either a rift valley, which is represented right here. So this big Eurasian plate and this big North American plate, they moved away. And so it caused these steep rifts, these steep valleys to form. Okay, so that's why you get these steep walls of rock all over the place. And you can kind of see like some little cracks are forming in between. So this is where these two plates separated. And so you get this really deep area. Now, when this happens underwater, okay, you get a mid-ocean ridge, okay? So what is that? That's where basically as the plates separate, okay, these are parts of the crust, there's hot mantle underneath that gets exposed to the cold water, and this causes it to cool down to form kind of like an underwater mountain. So that's what that is. All right, let's take a look at your different types of tides. Now, it's something important to know that your moon and the sun both control your ocean tides. How does that work? This is all due to gravity, and we won't go into the specifics, but just know that the gravitational pull of the moon is going to cause the water to move, okay? So this is going to give you your high tide and your low tide. So for those of you that fish, you know that the water levels move up and down. They don't stay in the same area. And no, this isn't talking about waves. It's talking about water level, okay? So during your first moon, during your first quarter moon and your third quarter moon, you can see here that the ocean tides lift up. But remember, the sun also plays a smaller role, okay? So the solar tide is a little bit smaller, okay? Now, what happens when the moon is aligned with the sun? So let's say this moon right here is right here in between the earth and the sun. That's when you're gonna have the highest tide, okay? So I'll repeat that. When the moon is in between the earth and the sun, that's gonna give us the highest tide, because guess what? The sun is pulling a little bit on the water. That gets us our solar tide. But the moon also pulls a lot on the water. So that's going to get us the lunar tide. So together, if they're lined up, it's going to create an even bigger tide. So that's important to know. Now, speaking of the moon, let's go ahead and talk about the different types of moons, different types of stages of the moon. All right. So first you have your new moon. This is when the moon is completely dark. Okay, so in that area, the moon is going to be right here in between the earth and the sun, right? Now let's talk about the waxing crescent. Anytime you hear the word waxing, what does that mean? That means that the lit up portion of the moon is growing. So waxing means growing, okay? So just remember that. Waxing means growing. If you remember waxing means growing, then you can remember what waning means smaller, getting smaller or decreasing. So just remember one of these. Waxing is growing, waning is decreasing. Remember one, and by logic, you can deduct or deduce the other one. So waxing means growing. So waxing crescent, then this is your first quarter. This is your waxing gibbous. Gibbous is going to be when most of the moon is covered. Crescent is this shape right here. Your full moon is going to be on this side of the earth. That's when the sun is shining on the moon, right? And you're going to have your waning gibbous, okay? Waning, again, meaning what? It's getting smaller. Then your third quarter, and your waning crescent. All right, let's take a look at the differences in our cell types. Here we have a plant cell, and here we have an animal cell. What's the difference? The main difference I want you to remember is that there is a cell wall. Now remember, both cells are going to have your cell membrane, but the plant cell is going to have an additional outer layer called the cell wall. Okay? Another difference you should know is that plant cells carry a large central vacuole. This is where water is going to be stored. Okay? This is where water is stored. Animal cells do not have that. Okay? If they do, it's going to be very, very small. Very, very small. Okay? Now, we're also going to take a look at chloroplasts. This is where light energy is turned into chemical energy for the plant. Plants have that. Animal cells don't. And just for fun, you already know the mitochondria is the powerhouse of the cell. This is present in both animal and plant cells. All right, let's take a look at biotic and abiotic factors of the ecosystem. Biotic factors are living, while abiotic factors are non-living. So anything that is living is a biotic factor. Keep in mind, anything that moves is not necessarily a biotic factor, right? Let's look at the water. The water moves. Now, we can be tempted to think that's a biotic factor, but water doesn't have life, okay? You have your birds and your fishes, your butterflies, the crab. These things are living. They move, but they are also living. Water moves, but it's not living, okay? So that's why it's abiotic. The sun is abiotic. The clouds are abiotic. The sand, abiotic, right? These are non-living factors, all right? Now let's take a look at our food chains. What is a food chain? A food chain is the flow of energy, right, from your producers all the way to your decomposers, or sometimes your final consumers. So let's take a look here. Here we're going to start off with grass. That's the producer. It gets its energy from the sun. Your producers get your energy from the sun, okay? Then from there, we're going to have the primary consumer. Typically, it's just labeled the consumer, but in this case, since we have more than one, you're going to see primary, secondary, tertiary, then final. That's just telling us that we have increasing levels of consumers. So energy is going to flow from the producer to the consumer, right? And some consumers eat other consumers, right? So in this case, we have a grasshopper, which is vegetarian and only eats grass. But then you have your frog, okay? That frog is going to eat the grasshopper, okay? So it's a predator. It's going to eat the grasshopper. Your snake is also going to eat the frog. So you see energy is flowing as we go higher and higher. Then the snake is going to get eaten by the eagle. Then eventually the eagle is going to die and it's going to be decomposed by fungi or other decomposers. Now sometimes you're going to have a food web. It's a bit more complex, but it's the same idea. Energy flows from your producers all the way to your consumers slash your decomposers. Okay? So in this case, we have a tiny food chain right here where the grass flows from the energy from the grass flows to the rabbit to the fox, or the energy flows from the grass to the mouse to the hawk, or the energy flows from the grass to the grasshopper to the bird to the snake, then to the hawk. So in this big food web, we have a lot of tiny food chains. All right, let's take a look at the scientific method. What is that? This is how we've arrived at most, if not, or not most, but all of the scientific knowledge we have today. Okay? How does it work? You have your question. So technically, first you have an observation. So you observe something and you think, how does this happen? Then we get to our question. How does light or the sun affect the growth of plants? That's the question. Then we make a hypothesis. Oh, maybe the sunlight gives energy to the plants. So maybe if the plants grow, let's say, in the sunlight, then we know that there's a relationship between the sun and the plant. So a hypothesis is typically an educated guess, and that's where you're going to get your if-then statement. Then you're going to do your experiment where you're going to plan and test your hypothesis. So you're going to put some of the plants in the sunlight, some of the plants in the darkness, and kind of see which one grows better. Then you're going to analyze, you're going to collect your data. Okay, so the plants in the sun, they grew at an average of 10 feet, while the plants in the darkness, they did not grow at all. Then you're going to analyze your data. So this is where you're going to say, this is an interesting pattern or an interesting trend in the plants that grew in the sun versus those that grew in the darkness. Then from that analyzed data, you're going to create a conclusion or report where you explain your result and whether your hypothesis was correct. Now, it's important to understand the difference between your independent and dependent variables. Your independent variable is typically what is being tested, okay? So here, this experiment says, does room temperature affect test scores? So what is being tested? Yeah, it's the test scores, but we want to see how room temperature affects the test scores. So temperature is going to be what we are manipulating, okay? So if I say, does room temperature affect test scores, I'm going to put some people in the cold room and some people in the hot room. Thus, your temperature is going to be your independent variable. That is what we are testing. That is what we are manipulating. And so this is the cause. So we look at cause and effect relationships when we look at independent variable versus dependent variable. So does the temperature cause the students to have good or bad scores? So are cold temperatures the cause of a good or bad score, or are hot temperatures the cause of a good or bad score? So again, as I said before, you don't need to remember both. Just remember one, and then you can deduce what the other one is. So if the independent variable is the one being tested, if that's the cause, then we know that the dependent variable is the effect. That's what we are measuring, okay? Let's take a look at energy transformation. We kind of went over this when we looked at the plant cell. So remember, light energy is turned into chemical or food energy for the plants in the chloroplast. Chemical energy for us in food is turned into kinetic or motion energy for us as humans. Chemical energy is turned into motion for cars. Electric energy is turned into thermal energy on the stove. So we have different types of transformation of energy. Lastly, we're going to take a look at renewable. I think this is the last slide. We're going to take a look at renewable versus non-renewable energy sources. Renewable sources, as you know, are the ones that we can get readily. This is renewable. Renewable sources are, for instance, your sun, your hydropower, geothermal, wind, and biomass. These are renewable in that they can be reproduced, okay? they can be reproduced. Your non-renewable energy is energy from millions of years ago, millions of fossils that have decomposed and have turned into oil or coal or gas. These are non-renewable. Why? Because we can't replace them so easily, right? Remember, oil, coal, gas, nuclear energy, all these things took millions of years to decompose and turn into energy. For us to harvest it again, we'd have to wait millions of years again. But the sun is always available. Water is always available. Wind is always available. Biomass is always available. Geothermal energy is always available, right? So that's why these are considered renewable. All right, guys, let's go over a couple of questions. This question says the chemical formula for acetic acid is CH3COOH. How many hydrogen atoms are in one molecule of acetic acid? All right, we have CH3COOH. Here, if we zoom in, we see we have an H3 and we have an H. What does that mean? This 3 means that this H, we're going to multiply it times 3. Okay, so we have one H times 3. That means we have 3 H's. But we have one more here. We have one more H. So that means altogether we have 3 H's plus 1 H. So we have 4 H's. We have 4 hydrogen atoms. Now, I want you guys to be prepared in case you ever see something a bit different. So let's say we have something like H2O. Let's say we have H2O. How many hydrogens do we have here? Well, we have a 2, we have an H. So that means we have 2 hydrogens, okay? We have 2 hydrogens. Well, what if we had something like this? We have 4 H, 2, O. What about this? Now, if you ever see something like this, pay attention to this 4 and this 2, okay? What does this mean? This 4 means we're going to multiply everything here by 4, okay? So before we had 2 hydrogens. We had 2 hydrogens. But now, because of this 4, consider it kind of like parentheses when you're in math. And it's a distributive property. So we're going to multiply this 4 times the H2 and the 4 times the O. So instead, we're not going to have 2 hydrogens. We're going to have how many? We're going to have 8 hydrogens. Because originally we have 2, but then we're going to multiply it by 4 to get us 8. Now, how many oxygens do we have? Well, originally we just have 1. But because of this 4, we're going to multiply it so we get 4 oxygens, right? So that's how you navigate this. Look at question 2. Here we have a table and we have a graph. How do we navigate this? Let's see. The table lists the characteristics of 4 stars. So luminosity, sun equals 1, temperature. Okay, so we have a graph. We have our x-axis at the bottom. We have our y-axis right here on the left side. Luminosity is going to be the y-axis. Temperature is the x-axis. Okay, let's see. How is each star categorized in the Hertzsprung-Russell diagram? I don't even know what that is, but we're still going to use what we know. So never let these big words fool you. They're just there to throw you off. Move the correct answer to each box. All right, let's look at the first one. Aldebaran. Okay, that's this one right here. What's the luminosity? 10 to the power of 2. Luminosity is right here. Let's look for 10 to the power of 2. This is 10 to the power of negative 4. 10 to the power of negative 2. This is 1. This is 10 to the power of 2. So Aldebaran is going to be somewhere along this line. Now, we don't just want to use that to guess where it is. We also want to use the temperature. 4,200 Kelvin. 4,200 Kelvin. Where is that? Let's take a look at temperature. So this is interesting. We're going from 40,000 all the way to 2,500. So it's decreasing going this way. So 4,200 is going to be somewhere around right here in between 5,000 and 2,500. So we have 4,200, and we have 10 to the power of 2. And if we trace them, we get this one right here. So we're going to put Aldebaran right here. All right, let's look at Altair. Lumosity is 1, temperature is 8,400 Kelvin. So lumosity 1, temperature 8,500, somewhere around right here, between 10 and 5. So this is perfect for Altair. Let's look at Betelgeuse. These are some weird names. Betelgeuse. Okay, lumosity is 10 to the 4. Okay. Temperature is 3,000. So probably around right here. 10 to the 4, 3,000 right here. So this is where Betelgeuse would go. Lastly, we have this one, but I just want to be sure. 10 to the power of negative 3 and 30,000. 10 to the power of negative 3, yep, probably right here. 30,000 in the middle right here, so yep, Sirius B goes right here. So that's how I would navigate this question. Let's look at question number 3. A student places ice cubes into a beaker filled with warm water. Which statement best identifies and explains the change that will occur to the ice cubes? All right, so before I even look at these answers, let's analyze what we just read. So we have our ice cubes put into a beaker with warm water. So if I put some ice cubes into a warm environment, what should those ice cubes do? The ice cubes are gonna melt, okay? The ice cubes are going to melt, okay? So let's keep that in mind. Let's look at our answer choices. So which statement best identifies and explains the change that will occur to the ice cubes? They will undergo a physical change to the state of matter from solid to liquid. I like this answer. Let's keep it in our back pocket. They will undergo a chemical change that permanently changes the shape of the ice cubes in the liquid. Well, we know that chemical change is irreversible. Physical change we can reverse, and we can reverse the melting of ice cubes from solid to liquid by simply putting the melted ice back into the freezer. So chemical change is a no-go. So B and D are both wrong. So now we're left with A and C. They will undergo a physical change caused by a transfer of heat from the ice cubes to the liquid. Okay, let's read that again. They will undergo a physical change caused by a transfer of heat from the ice cubes to the liquid. Well, let's see. Is heat flowing from the ice cube to the liquid or from the warm water to the ice cube? Let's think about it. If heat is flowing from the ice cube to the liquid, that means the ice cube is warming up the water. But ice can't do that. Ice is cold. So therefore we can deduce that A is a better choice. Now, C would have been an okay choice if this was phrased differently. The heat isn't going from the ice cube to the liquid. It's going from the liquid, the warm water, to the ice cube, which is causing it to melt. So that's how I would analyze question 3. Question 4. A class is making a poster about the sun. The poster includes drawings and information about the sun. Which statement should students include on the poster? The sun has a solid rocky core. Does the sun have a solid rocky core? Let's check our different answers. B says the sun is one of the largest stars in the universe. Okay, interesting. Let's check out C. The sun is farther from Earth than some other stars are. Well, the sun is the closest star we have to the Earth. Okay. The sun is located on a spiral arm of the Milky Way galaxy. Well, we know that we live in the Milky Way galaxy. So I think D is going to be the best choice for us, right? Now, this is just done by simply eliminating weird answer choices. So the sun has a solid rocky core. Well, we know that the sun is composed of a big ball of gas that is currently just it's currently just combusting, okay? So it's a big ball of hydrogen and all these other different gases, and it's just being lit on fire. So it doesn't have a solid rocky core, okay? The sun is one of the largest stars in the universe. Well, we don't believe that. The sun is one of the stars in the universe, but it's not the largest. There are many other stars in the universe that are way bigger than our sun. Also, the sun is farther from Earth than some other stars are. Well, we know that the sun is the closest star in our universe. Okay? I mean, at least in our galaxy, right? And the sun is located on a spiral arm of the Milky Way galaxy. Well, we know that we are in the Milky Way galaxy, and so that's where the sun is located. Let's keep moving. All right. Students use a cart and some cargo to investigate acceleration. The diagram shows the available carts, each cart's mass, and 3 types of cargo that can be used in the investigation. The wheels on all carts are identical. So you have cart 1, which weighs 0.125 kilograms, cart 2, which weighs 0.2 kilograms, and cart 3, which weighs 0.225 kilograms. We have bolts, which are 1.25 kilograms, sand, which is 1.5 kilograms, and coins, which are 1 kilogram. Okay, let's look at our question. If an identical force is applied to all the combinations of cart and cargo, which table shows the combination that produces the least acceleration and the combination that produces the greatest acceleration? All right. Before we do this, we must understand what force is. Force is mass times acceleration, okay? And we are using an identical force. So for questions like this, I like to kind of write out what I'm working with. So we have force is equal to mass times acceleration. Okay. Now we are using an identical force. So let's say I have a force of 10. Now we want to see what gives us the greatest acceleration. So what 2 numbers can I use to multiply to get us to 10? Well, I can use 2 times 5, right? Okay. Well, let's change this 10 to 20. Let's change it to 20. So 4 times 5 gets us 20. So if I have a mass of 4, okay, mass of 4, and I have an acceleration of 5, I still get the 20. But we want to find the combination that gets us the smallest acceleration, the least acceleration, and the greatest acceleration. So how do we do that? Well, to get the biggest acceleration, what do we need to do? What's the biggest number we can use to get to 20? Well, we can do 20 times 1, right? So in order to get the biggest acceleration, our mass has to be very, very, very small, okay? But what if I want to get the smallest acceleration? Well, we can do that too. 20 is equal to 20 times 1. So if I want to get the smallest acceleration, I would need a mass that is very, very, very big, right? If I want to get an acceleration that's kind of mid, I can do 4 times 5. It's in between, but it's not the smallest or the greatest. It's kind of mid. So in order to get the smallest acceleration or the greatest acceleration, we need a mass that is either very small or very big. So let's keep that in mind, okay? Let's keep that in mind. So to get the least acceleration, what do we need? We need a mass that is very, very big. So we need to combine carts that are very big and cargo that's very big. So let's take a look at our answers. So to get the least amount of acceleration, they're going to use cart 1. Is cart 1 the biggest cart we have? No, it's not. 0.125 is the smallest. So this will kind of give us like a mid acceleration. We want a small acceleration. Let's take a look at B. To get the least acceleration, we're going to use cart 2. But is cart 2 the biggest? No. Cart 3 is the biggest. Looks like answer choice D uses cart 3. Let's see, does it also use a very heavy cargo? It uses cargo Y. That is the biggest. So therefore, D is looking like a good answer. Let's check the greatest acceleration. It's going to use cart 1 and cart Z. So to have a really high acceleration, we need to use a mass or a weight that is very small. So they use cart 1, which is the smallest cart, and cargo Z, which also is the smallest cargo. So therefore, D is the best answer. Look at one more question. Question 6 says, this question has 2 parts. The model shows the movement of 2 continental plates. So these plates are moving together. So this would be a what type of boundary? It would be a convergent boundary. Okay. Which geological feature is most likely to form along the plate boundary? All right. So we have a mountain, mid-oceanic ridge, trench, and rift valley. Now consider this. These are continental plates, not oceanic plates. Continental plates are going to be on dry land. Oceanic plates are going to be under the water. So already we can eliminate B and C because these are geological features found underwater. Okay? You have your mid-oceanic ridge and a trench, which is underwater. Now we have a mountain and a rift valley. Which of these is likely going to form from this boundary? This is a convergent boundary, so both of these boundaries are coming together. So a mountain is going to form, not a rift valley. A rift valley is formed when 2 plates move away from each other. Part B says, which statement best supports the answer to part A? Now we know that this is a convergent boundary, as we recently discussed. So answer choices B and C are not it. Answer choice A says, at convergent plate boundaries, one plate slides underneath another plate. Yeah, this is true, but that's not what is giving us our mountain. At convergent plate boundaries, the plates are folded and pushed upwards. Yes, this is what we get here. So therefore, for question 6, part A, we get A, and for question 6, part B, we get answer choice D. Alright everyone, that brings us to the end of today's video. If you found it useful, I'd really appreciate if you could give this video a like. Also, maybe share it to a student that could maybe benefit from this type of content. Remember, in the future, we are going to other grade levels for STAAR test prep, so make sure to subscribe so you're updated when we do release those videos. Also, if you'd like one-on-one tutoring for your student, don't forget to check the link in the description. There you can access the sign-up link for Checkmate Scholars. Remember, for new Checkmate Scholars customers, you do get 1 hour of free tutoring, so don't let that opportunity pass you by. Sign up today. As always, I'll see you in the next video. Until then, checkmate.